All right, hello everyone and welcome to the Warning Decision Training Division's new webinar series, R2O O2R Tales or Roots. This was formerly known as Tales from the Testbed. I am Jessica Blair of OU Serial. I'm here along with Kevin Thiel of Serial and SPC and Lexi Elizalde, also of Serial WDTD. Today we'll be going back to our roots with a Tales from the Testbed style webinar broadcasting live from our WDTD conference room. We have several visiting forecasters here who will discuss their impressions of the new satellite products as part of this year's Satellite Convective Applications Experiment. Our distinguished guests this week are Christina Amiot from NWS Huntsville, Alabama. We have Robert Haynes from NWS Burlington, Vermont, Alex Edwards from Tucson, Arizona, and Andy Hatzos from Wilmington, Ohio. I will now turn things over to Kevin Thiel. He is the lead investigator for this experiment to introduce the EWP and the experiment, and then we'll hear from our visiting forecasters.
Thank you, Jessica. So the Satellite Convective Applications Experiment is part of the HWT's Experimental Warning Program, or the EWP. And so the mission of the EWP is to be able to improve our hazard weather forecasting capabilities, whether it's developing technologies, new techniques, and training, and to be able to provide those then and evaluate them for stakeholders from observer applications, observing platforms, and to be able to evaluate those technologies. We can take the expertise that we have here in Norman with all the entities you see there on the right, in addition with the expertise that we have from across the Weather Service and from cooperative institutes, along with universities and other NOAA facilities and as well to partner to put on this kind of a test bed and this kind of a program. And so this for us allows us to complete the research to operations and operations to research loop, where we're able to provide new technologies and feedback from the forecasters, and then that can turns around and is either placed into operations or helps to inform things like training or new avenues of future development and research that is needed for these communities. So we are a live test bed, and so we go where the weather goes. And so throughout the week, we had our forecasters at simulated WFOs. They were providing not just convective monitoring and also issuing warnings when needed. They also provided decision support as well for simulated events, and you'll see a few of those mentioned throughout the presentation. So as we traveled along throughout the country there, we were at the Central and Southern Plains, but we looked at the 5 products this week in all of these different scenarios in a pretty active pattern this week. So I'm going to go through the 5 products, briefly explain those, and I'll turn it over to the forecasters and let them talk about their experiences and then their reflections and their takeaways from each of those products. I will start with the GLM background and data quality product. So the GLM background is actually the background image taken from the geostationary lightning mapper, which is used as a reference point then when it's looking to detect flashes. That is additional information there and is able to show things like the subarray boundaries and the local relative brightness in which the GLM is referencing when it's then looking for the changes in brightness for those flashes. Additionally there, you can see in the top right image, that's an example of the data quality product. So the changes in brightness can help them correspond as well to the flash detection efficiency, and those can then be changed throughout that scene. Additionally, you'll see in the white and yellow pixels there that are lit up, those are actually pixels that are at or near saturation. And so forecasters had this information available to them this week to then understand the GLM gridded imagery products like flash extent density to be able to interpret that imagery in real time. The next product is Gremlin. Gremlin is a radar estimation that only uses satellite data. So we're looking at information from the advanced baseline imagers, 2 shortwave infrared and 2 long-wave infrared bands, along with group density information from the geostationary lightning mapper. And so this provides an estimate of the MRMS composite reflectivity in an area across the country, spatially uniform, and provided even in areas where you either have degraded radar or maybe no radar coverage exists in those areas. This was provided for forecasters across the full disk image, so updating every 10 minutes. They were able to look at these data throughout the week. Third here on the list is Octane. Octane provides high-resolution cloud-top wind retrievals from the textures and the gradients that are moving in the AVI mesoscale scenes. So those update every minute, so it's very high spatial and temporal resolution. And so from the gradients observed in the visible and the infrared wavelengths, this provides cloud-top wind retrievals for speed and direction. And those are things we tested last year. This year, in addition, you'll see a divergence in a cloud-top cooling product that were also calculated as well in Octane and provided for the forecasters, and a few different overlays and flavors for them this week. Rounding out our list of products here, we also have the PHS model. Now, testing a model in a satellite experiment may not sound intuitive, but actually this model provides a novel data assimilation technique. And this assimilates these hyperspectral sounding profiles along with information from the AVI into a 4-kilometer WRF model. And then it's able to adjust those profiles and to provide that as a kind of short-term nowcasting technique as well, and to support mesoanalysis. So how the information from these hyperspectral sounders can then influence the model output and what can be compared against things like the HER or the RAP or other cams. Last year on our list is Prob-Severe Lightning Cast. Prob-Severe Lightning Cast provide lightning probabilities over the next hour by using only EVI imagery and using 4 select bands in that imagery. Products that are output from that are the probability of more than 1 flash over the next hour, or the probability of greater than 10 flashes over the next hour. So the first one is for any kind of lightning and any kind of initiation of lightning you would have. The next one is for especially those storms that were more intense, and they get pickup that you would have as those storms intensify. Additionally, there was a lightning cast dashboard that displays that information at specific points that forecasters could submit a form for and get those readouts of the probability of those lightning flashes greater than 1 or 10, in addition with the GLM imagery. And they could provide that information as well in terms of a range ring around a point. And so forecasters were able to put those points at their simulated DSS events throughout the week. So that's a rundown for the products. So I'll turn it over to the forecasters and let them talk about all their products and the feedback that they've had on throughout the week.
Hi, I'm Alex Edwards from WFO Tucson. I'll cover the Octane product here briefly. Octane stands for the Optical Flow Code for tracking atmospheric motion vector and nowcasting experiments, but as Kevin mentioned, it essentially gives context to the motions of the pixels retrieved from AVI, both in visible and infrared at those levels. Last year at the hazardous weather test bed, we looked at the speed and direction of those pixels out at the cloud tops. This year we added divergence and cloud top cooling. This created a really neat way of tracking both developing updrafts and cloud top characteristics of already mature thunderstorms, which allowed for a non-radar way to track the evolution of a thunderstorm, either adding confidence to our radar analysis or providing assistance in the case of radar outage or poor radar quality. In the top image there, that's the cloud top divergence and cloud top cooling product displayed together. The purples and pinks are the cloud top divergence part, and you can sort of make out where the stronger cloud top divergence signals are shown with the more consistent purples and then more intense pinks there, the ones that are more grouped together, especially on the up shear side of that tornado warning. And then also if you squint, you may be able to make out the cloud top cooling signals in the lime green, especially in the bottom part of that top image, in that severe warning, and then also on the top of it. These lime green and even yellow to red in the more intense cases. Colors corresponded with overshooting tops or intense updrafts, showing signals for further intensification or initial intensification. Both of these together gave us a good look at what a thunderstorm was doing. And then on the bottom image, this is cloud top speed, I believe, but using the IR bands. So using the IR bands to be able to track the speed of those cloud top pixels, which allows for this kind of tracking tool to be used at nighttime as well. But also it was very helpful during the daytime. You can see there in the bottom left, the blues showing up on the upshear side as divergence near the updraft was really highlighted in this thunderstorm, as at the time it was producing quite a bit of severe hail, wind, and I believe at some point was even tornado warned during this experiment. Just a couple examples here of developing updrafts using cloud top divergence and cooling products. In the top left is an orphan anvil process where the initial updraft is shown with the cloud top cooling in the greens, yellows, and reds at the most intense. Even though it wasn't able to take root at that time, it still produced a little anvil cloud moving off to the east there, which was then highlighted by that cloud top divergence product. So you can really see the whole evolution of this orphan anviling process highlighted by the cloud top cooling and divergence product. It just allows for extra confidence in what you're seeing, highlights the tallest cumulus towers there at the moment. And then in the bottom image, a more mature version of the same process as thunderstorms initiated and developed. You can see the greens, cloud top cooling, the greens, the yellows and reds, and then giving way to the cloud top divergence signals with the purples and pinks, while those greens still show up there as those powerful updrafts are pushing through. So both the cooling and divergence products were very useful this week in identifying thunderstorm initiation and severity. And I found they could be used for not only just situational awareness of your overall scanning strategy and warning operations, but it could be used as well for severity analysis, both in conjunction with radar and also in cases where poor radar coverage was in place, as those cloud top divergence signals generally correlated with more severe thunderstorms, especially in the right environment.
All right, so I'm Robert Haynes from the National Weather Service in Burlington. I'll discuss here the Polar Hyperspectral Sounder. These are tools that are on low Earth orbiting satellites to provide additional moisture and temperature data to high-resolution models. So this information that is acquired from the Polar Hyperspectral Sounder is incorporated into a 4-kilometer warp that runs a similar configuration to the HER. So with this, it offers the forecaster the opportunity to look at these short-term updates to the forecast that are based on the augmented satellite moisture that comes from the PHS. So as with any polar orbiter, it's passing through different sectors of the United States at different times. And so from those polar orbiters, that information is taken from different sectors at different times, but it's still run at an hourly rate. So this provides a unique method of comparing the PHS with, say, the HER, and allows the forecaster to maybe compare and contrast the initiation and the evolution of thunderstorms in their near-storm environment that is augmented with this data from the PHS sounder. So on the right here is an example of one forecast using PHS data. It depicts a line of convection that's shifting into Iowa and the Cape and the 0 to 3 kilometer storm relative helicity that's shown in the white contours. And so looking at this event as the linear convection was evolving, we were able to see how this initial line would then begin to rotate as time went on through the event, as stronger instability and storm relative helicity developed ahead of the boundary. And so with that, we could start looking at the storm evolution and determining, okay, maybe winds and hail are the first threat, but over time, as the line begins to have more embedded rotation, then tornadoes would become a more significant threat as the line evolved. As with any mesoscale model, we did notice that there was still at least some bias as far as the late convective initiation. It still performed maybe about an hour or two faster than, say, the HER, but occasionally it would still be prone to late convective initiation as well as convective feedback. And so the primary takeaways is that this offers an additional data set to be ingested into high-resolution models that forecasters can analyze. On the web page, there are even opportunities for forecasters to look at the RAP and the satellite data as well to compare the difference that the satellite data offers to the RAP or the HERF forecast. And so this gives forecasters additional information about the near-storm environment and their expected evolution. It offers something that's very unique and I think could be beneficial to forecasters who are trying to understand the environment their storms are growing in. It does have similar pitfalls. It's not going to solve every problem that the high-resolution models have, but overall, a very useful model, I think, for forecasters to use.
Hey, this is Alex Edwards from Tucson again. I'm going to cover quickly the GLM background and data quality product here. GLM background here is essentially what you see in this animation, especially the satellite-looking product here, because that's essentially what we're looking at is clouds from Texas to Oklahoma City. And the background product is used as essentially the baseline for GLM to observe those optical flashes and then produce the flash extent density product or other GLM products that operational forecasters are familiar with. The GLM background image here could potentially be used as not a replacement, an extreme backup for the ABI in case it was ever unavailable. We can see the spatial extent of clouds in this image even if it's at a coarser resolution. One important aspect that we were looking at this week was the existence of the subarray boundaries, which are the east to west stripes you see on the map here, and that's just the overlap in the GLM subsensor coverage, those sensors that are looking for those optical flashes. And those boundaries can impact how the GLM mapper displays flashes because it'll be more sensitive along that overlapping boundary that we see. Additionally, we looked at the data quality product, which highlights those areas which potentially have maybe flashes that approach or reach saturation of the brightness level, and we used that product to gain confidence or add context to the GLM flashes we were looking at this week. So the combination of the subarray boundary and the cloud tops can saturate GLM, which can create false flashes in regions where that subarray boundary and active weather coincide. A common one is the Bahama Bar artifact you might have heard of. And there is processing to handle this, which then inversely GLM data can potentially downgrade along that subarray boundary during certain situations because of the filtering from that processing. For example, that might happen near solar noon, depending on what part of the country you're in the right situation. So this data quality product that you see like in the bottom right, it will light up in magenta, or however the different color tables we looked at this week is used operationally. If that case is happening, which can signal to us that the GLM flash we are observing in operations may not be quite correct or what we're used to and require a little further interrogation or maybe just a grain of salt in our operational use. And so that was what we looked at this week. And then as I mentioned, kind of the additional takeaway was that GLM background image does provide kind of a visible satellite proxy that could provide that backup satellite image in the case of ABI failure, though it is at a much coarser resolution. But it does provide a spatial cloud extent image that can be used.
All right. Hi, everyone. I'm Christina Amiot from WFL Huntsville. I'm going to be talking about the PropSphere Lightning Cast, and just bottom line up front, I feel like this tool would be a great resource to use for DSS, not just for on-site, but also for remote weather watches at the WFO themselves. So I'm just going to go through an example here. The Aberdeen CWA, we were assigned our IDSS event at a fishing derby, which you can see there, surrounded by a yellow range ring, which is 10 miles from the center. And what I have here is I have the visible satellite, and the colors you see there are the chances of a flash within 60 minutes. And then if you can kind of see, especially in the top right of the animation, those like red and pink contours that show up, that's probability of 10 or more. And then also I have GLM pixels and the ground network showing up on here too at times. And then on the lower right there is an image of the dashboard that we tested as well. And so from this example, this data, I was able to provide a DSS message that we were noticing an uptick in lightning probabilities due to the storm cells developing to the south and southeast of the Derby, which again is that yellow range ring, and those were moving northeast. At the time, those were not severe and lightning had not been observed by GLM or the ground networks yet, but the probabilities of lightning within the 10-mile range ring were between 40 to 50%. And that was shown on that graph as well. It's kind of that like pinkish line that goes between 40 and 50%. So eventually lightning had been observed, but before then, when the 10% contour line, which is that little red spot there, which was a 10% chance of 10 or more flashes, when that first popped up at 2010Z, it was 10 minutes until GLM and the ground networks observed flashes, which can be seen in this next image here on the left with the blue pixel showing up, and the ground network should be in magenta. It might be hard to see here, but 5 minutes later, that is when the ground networks observed CGs. And so in terms of lead time, when I crafted that DSS message, it was about 3:10 to 3:15 or so. And the first flashes were observed at 3:20 and CGs at 3:25. So this tool gave about 10 to 15 minutes or so of lead time. And this is another update. Just wanted to show the LightningCast dashboard showing those GLM flashes within 10 miles, which are the blue dots you see in the middle between the two lines there. So key takeaways. LightningCast can help forecasters with messaging the lightning probabilities for on-site DSS, but also during remote weather watches at their own office. For me, one of the most important things here, the LightningCast probabilities can provide lead time to the onset of lightning, which would be absolutely invaluable for our DSS and to our partners. And if I were to use LightningCast while at an on-site deployment, and if a partner wanted to look at this data, I'd make sure while I'm showing them that dashboard graph, because that's a site-specific, you can insert the lat long for that specific site, and it'll show, the data will show up on there. Would also show that map view I was showing you in order to give more context to the overall environment, the storms, and just the trends going on at the time.
Hello, this is Andy Hatzos with WFO Wilmington, Ohio. I'm looking at Gremlin, which is the GOES radar estimation via machine learning to inform NWP product. It is essentially a synthetic composite radar reflectivity product that is generated using a convolutional neural network trained to match MRMS based on satellite data. It's looking at multiple wavelengths from the ABI in addition to GLM to basically create an image of what the radar data may look like underneath that satellite information. And it is calibrated to composite reflectivity. So in this first example, you can see it has a predictive element to it. On the left, you see Gremlin, which is depicting an area of an isolated thunderstorm in Texas. The far right, you'll see one of the nearby radar sites, composite reflectivity from the radar. And both the Gremlin image and the composite reflectivity from the radar are showing that there is indeed convection there with echoes of 50 plus dBz. You'll also notice that the middle is our base reflectivity slice off of that nearby radar in Texas, showing only very light echoes at that time. So because Gremlin is trained on comp reflectivity, if you have initiation going on, Gremlin can often pick up on where storms are developing a little quicker than you would see things at the lowest slice of a nearby radar. It was either this storm or another one in the same area ended up becoming a splitting supercell, and we wanted to examine how Gremlin performed in a splitting supercell case. So if you're looking at the radar images, let's just use the middle screen, which is the nearby radar low slice, you can pretty clearly see the split occurs. You have a very well-defined right mover that tracks to the east-southeast, and then a left-moving cell that tracks to the northeast. And we wanted to sort of look at how Gremlin would pick up the two cells. You can see in the very last frame, Gremlin does have both cells depicted, but Gremlin is a little bit slower in depicting that left split as it's occurring and as you're seeing it on radar. So we wanted to take a closer look at why this may be the case, why Gremlin might have been a little bit slow to pick up on that, and if that has applications for how Gremlin is going to be used potentially by forecasters in the future. So what we did was decided that since we're in Texas, we're sort of in a place where we have a decent view from both GOES instruments. Let's look at GOES East and GOES West for this cluster of thunderstorms, this splitting supercell. So if you look at the GOES East imagery on the right side, you can clearly see a big anvil with an overshooting top as this right mover moves to the east-southeast. What you can't see so well on the GOES East conventional imagery or the day cloud phase is what you can see on GOES West with it, which is that you have a separate updraft associated with that left mover that is peeking out from under the anvil from GOES West's view, but not so much from the view that GOES East has. So Gremlin is running off of both GOES West and GOES East, so we decided to pull up both versions of Gremlin and compare the two. GOES West Gremlin, because it's able to see that updraft better, it's not blocked by the anvil from the right mover, it's able to see the left moving updraft better. GOES West Gremlin does depict that cell a little bit quicker and a little bit more accurately as it moves off to the northeast. So this is good just to remember, not just for these new experimental products that we're looking at, but in general, GOES West versus GOES East have different views, and the viewing angle is important to consider. You may, as a forecaster, find useful information by looking at both GOES East and GOES West, or derived products such as Gremlin from both GOES West and GOES East. So just a few other takeaways is that Gremlin is, as a synthetic radar product, is something that's going to be useful in cases where radar is either degraded or you're a long distance from radar, where it might be useful to have some sort of derived radar product, again, based on machine learning, based on how satellite appearance is from multiple wavelengths and from GLM data. So that can be useful in cases where you're a long distance from radar, or maybe your radar is down. In extreme cases, it may be something that you could use to help issue warnings. You would want to combine Gremlin with other non-radar sources, of course, such as lightning data. Perhaps you've got some surface observations, just to improve your assessment of where exactly Gremlin is depicting the storm, location, strength as well, just so you can get a little bit of a better idea. Gremlin may or may not exactly put it in the right place. It's not parallax corrected, so you may have to calibrate yourself just a little bit on that. The simulated reflectivity values off of Gremlin are calibrated to comp reflectivity from MRMS. We've usually found they are a little lower than what ends up verifying with radar or MRMS, rather than maybe, not a huge difference, maybe 5 to 10 dBz in most cases. We saw a few cases where Gremlin was pretty much right on as well, but typically it'll verify a little lower than your radar DBZ values. And it does perform best when you have sharp gradients and a lot of texture in satellite imagery, which is typically going to be early on in the life cycle of a thunderstorm. When convection is mature, you have lots of cirrus blow-off, big anvils. You can sometimes lose detail with Gremlin. Gremlin isn't able to quite pick out the individual storm cores as well. We had an example with a north-south oriented band, a broken band of thunderstorms, where at the southern end where you had cleaner updrafts, Gremlin was doing a very good job picking out each individual core, each individual cell, and then as you went further north, then you had much larger anvils and cirrus blow-off also sort of impacting the view of the satellite, and the textures were not as clean. Then Gremlin would sometimes maybe miss a cell or two, or maybe combine multiple cells into what it was depicting as a single line of thunderstorms. Regardless of that, we did think that Gremlin has a good bit of use when you have cases where you may end up needing something to give you an idea of what radar might look like.
All right. If any of you have any more questions, or if you're looking for more information regarding the hazardous weather test bed, we do have the website and the link to our blog linked here below. Lexi will help facilitate the Q&A session today. Lexi, do we have any questions?
We do. Our first question that we have is for all of you. Do you think Gremlin would be useful over an open ocean, perhaps to alert ships to strong convection?
I believe so, yeah. Yeah, no, I definitely think it would be. Yeah. Of course, all the cases we used were over land, but I think it was calibrated well to severity of like the reflectivity, so you could correlate that to what might be like the maritime hazard. So I don't see why not.
What is the cadence of the GLM background images?
The cadence of the background images is currently 5 minutes is what was delivered to the forecasters this week. So it roughly coincided with what you would have from the ABI CONUS scene imagery.
Which product do you think would be most applicable to your office?
I think the Octane product I found to be very, very useful because it helps me to understand the motions that are going on in the atmosphere. The atmosphere is a fluid, and it's really nice to be able to see at cloud level some of the speed and directional changes that can go on within thunderstorms. So anything that helps me to understand the way the atmosphere is moving can impact in a positive way my ability to forecast and warn for storms. So I thought Octane was very useful and could be useful like right away.
I agree with what Annie said, and even just tracking the maintenance of severe thunderstorms or new ones would be really useful from a warning perspective. From a DSS side of the house, I really, not just because I talked about it, but I really enjoyed the lightning cast from a DSS perspective. I think that would be a really useful tool for an on-site or even, like I said, a remote weather watch perspective.
And one of the other things we got to test was using Goes East. We had the ability to look at the probability of 10 flashes as well. In some cases, using that probability of 10 flashes was a really helpful way to pinpoint where more severe updrafts might be about to take place based on the satellite data.
And from my perspective, coming out of Tucson, I think all of these are definitely useful. The ones that are highlighted for me are ones that would be useful in the cases of poor radar coverage, or if we have a radar down for whatever reason. But in Tucson, we do have mountains that block radar coverage over towns. So anything like Octane, lightning casts, even Gremlin can give us confidence in areas where we don't have traditional radar. And that includes being up against Mexico where they don't have a radar network. We do have convection moving out of there, or even heavy rain on the other side of the border that do flow northward with water that flows northward into the Tucson area. So definitely useful in western regions as well.
When might we see Octane and AWIP?
That's a great question. So Octane right now is still in the development cycle, and that's something that how that would get into AWIPs in an operational sense, I don't have a great answer to that question. A lot of what we do here is been pushing things forward and letting Weather Service and those that are able to then make those decisions on what goes into AWIPs, able to make more effective decisions. If you would like to view the Octane products, you can actually look at them right now on the Sierra Slider website. Those are available as long as you make sure that you select them as a scale scenes and scroll down to the experimental products. You can look at those today and right now and those are running live for those products. So while AWIPs availability is something that it's a little unknown as of right now, but you can view these products online through the Sierra Slider website.
Oh, we have an answer also to that as well that says likely whatever cloud AWIPs is introduced.
Yeah, the capability as well, especially data flows and what they're able to do in terms of especially bandwidth. That's one of the things with Octane is a product that is being very, very high temporal and spatial resolution. Is one of the other aspects of it is that also means that it's large in terms of its files and data delivery too. So providing a lot of information, but that is something like a cloud AWIPs being able to more efficiently handle that data and distribute it to the weather forecast offices in a future configuration. Don't know what exactly that would look like, something along those lines.
For the PHS, did you compare the operational work without PHS versus the research work with PHS? If so, how did they compare?
We did do a few comparisons. In general, we found that it was usually a little quicker to initiate convection than the HER, There was still a little bit of a late bias, but it was better usually than the HER for the initiation of convection by about an hour. As far as the ability to then resolve the evolution of the storm, the performance was relatively similar. So we saw the biggest advantage in the initiation of convection.
I don't think we compared operational water.
Not directly to the water. No, from what we made available to the forecasters, I think the biggest one was the HER, and then also just viewing the SPC mesoanalysis online without a point of comparison.
All right. Thank you, Kevin, Lexi, our visiting forecasters, as well as the developers who helped out with this experiment. We want to thank you all so much for joining us today. We hope you'll join us for future Roots webinars. So we'd like to say thank you again. Have a great afternoon and have a great weekend, everyone.